Capacitive voltage divider. Capacitive voltage divider is used to reduce the voltage level to the measurable value. It consists of high voltage electrode, grounded electrode, and the output terminal that is connected to the voltmeter. Capacitive voltage divider can be used to measure static, AC, and transient voltages, and the maximum allowed voltage is 400 kilovolts. My task is to calculate electric field stress distribution and the voltage at the output terminal. The geometry model features rotational symmetry, so I am going to build two-dimensional axisymmetric model in QuickField. Okay, let's start QuickField now. In QuickField, I create new problem. Divider. Next, problem type is electrostatics. Divider features rotational symmetry, so the model class is axisymmetric. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw a geometry model here, or you can import the geometry model from the AutoCAD.exe file. I already have the drawing prepared in the CAD system, so I will import it. Here is the model. In axisymmetric problems, the axis of rotation is a horizontal one. So switch to select objects mode, select everything, edit, move selection, rotation by 90 degrees. And switch to insert mode and draw the axis of rotation. Now again switch to select mode and select and remove all objects located below the axis. In fact, the electric field is distributed not only in the insulator but also in the air outside. So we need to add the air block here. QuickField cannot calculate field distribution in the infinitely large space, so we should limit the simulation domain. And I will draw the half arc here. Zoom to fit. Now let's assign labels. Through labels you can explain the geometric object's meaning and provide material properties. Switch to select objects mode. Click the object to select and type in the label name here. This is air. This is insulator. This is some plastic. Now let's zoom in. Here we have the grounded electrode. Here we have the electrode that is connected to the voltmeter and the insulation layer in between. In fact, there is no electric field inside conductors, so I'm not going to assign label to the electrodes. Instead, I will assign label to the electrode surface and specify electric potential. Zoom out to see the entire electrode. Now I use the rubber band to select the electrode. Let's zoom in. You see the border, the edges, and the vertices are selected. I need to assign label only to the edges. Grounded. And the same I do for the electrode that is connected to the voltmeter. Again, use the rubber band. Let's check what I have selected. Alright, and assign label to the edge voltmeter. And I need to assign label to the high voltage electrode surface. Edge high voltage. Now let's provide physical properties for these labels. Double-click the label name in the tree. Electric permittivity of the air is 1. Electrical permittivity of the insulator is 2.3. Electrical permittivity of plastic is 4, and electric permittivity of insulation layer is 3.2. Grounded electrode has 0 electric potential. High voltage electrode has electric potential of 400 kilovolts, and voltmeter electrode has unknown potential. It's floating conductor. Geometry model and material data are ready. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Save all problem files and solve the problem. Let's take a look at the results. Here you can see the electric potential distribution, grounded electrode, high voltage electrode. I'm interested in the electric field stress distribution. Now let's zoom in and take a look at the most stressed parts here. And the electric field stress value here is, let's use the local values tool. Click here. Okay, this is the electrode and this is the electric field stress value. 39 megavolts per meter or 39 kilovolts per millimeter. Let's zoom out and adjust the field range. I would like to see areas where the electric field stress is above the electric field strength of the air. So the maximum value is 30 kilovolts per centimeter, 3 megavolts per meter, right? Now in these areas, the red ones, the electric field stress is above the electric field strength of the air. So you could expect to have here corona or some partial discharge. Okay, and my second point of interest is the potential of the voltmeter terminal. Let's zoom in. This is the grounded terminal and this is the voltmeter terminal. Again, let's adjust the field picture. Grounded voltmeter. To measure the potential, I will use the contour tool. Just click the electrode surface. You see, this is this red line. The electrode surface was selected. Now I can take a look at the XY plot and the exact value I can see in the table. So using the capacitive voltage divider, we were able to reduce the electric potential from the 400 kilovolts to a measurable value of about 1 kV. If you search for the capacitive voltage divider on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.